probability, and then transition probability basically just gives you the probability of starting from state S. What if you take action A? What's the probability that you will land in state at S dash? Okay. And then the reward function, all it does is that it tells you given some state S and some action A, what's the reward you'll get if you take that action from state S. So that's an MDP. And so the way that we represent an MDP in a diagram is that for state, we write, or we draw a circle for state. So imagine if you have 3 states, S, T, and U, you literally just draw 3 circles, S, T, and U here. And then actions are represented as a square. So suppose from state S, you can take an action A. Then I'm just going to draw a square A here and drawing an arrow from the state S to the action A. And this arrow here, if there's a number next to the arrow from the state for a state to actions, then that number represents the reward that you get. Okay? And I think the convention in this course is that if there's no label for that edge, then that means that the reward is 0. So I can either put a 0 here or put nothing down. Okay? Now, the other arrow, which looks exactly the same, but if there's an arrow from an action to a state, that represents the transition probabilities. Okay? So if I draw an arrow from action A to state T, and I put 0.5 here, what this means is that the transition, if you take action A, there's a 50% chance you will land in state T. And there's another 50% chance that you will land in state U. Okay? And then you can keep doing this. But this is kind of the general idea. Okay? So here I'm just trying to reproduce the diagram in the first diagram of the tutorial. Maybe let me just go one more step, and then I think you'll get the idea. So suppose now I start from state U, I can only take one action, and that's called that action B. Again, an action is a square. If I take this action, suppose I get a reward of 1, then I would put 1 here. And then suppose that when I take action B, there's a 70% chance I might land in state T, then I would draw it like this. And then if there's the remaining probability I might end up back in state U, then this will be a loop back to state U with probability 0.3. Okay. So I hope that's straightforward. So if you have questions about this, just post it on the chat box. Okay. So we're gonna use this convention, this diagram, to answer a lot of the questions. And so let's actually move on to the actual first questions of the tutorial. Okay. So the first question, and I guess if you understand how the diagram works, the first question should be fairly straightforward. And all you have to do is to translate the description of that's presented in question 1 into a diagram. Okay? And so as you read through this question, really the question that you have to ask yourself is, what are the states and what are the actions? And once you've got that, and then the transition probably should be easy to derive. Okay, so let's actually read through the question together. Okay, so we have an MDP representing a prehistoric nomadic tribe. Now, in each state, the tribe can either hunt or not hunt. Okay, so straight away, just with this sentence, you know that there are 2 actions: hunt or not hunt. And then the state also have to eat as well. But then the question explicitly says that we don't need to represent the eating as an action. So there are 2 actions, hunting or not hunting. Now, the tribe's food supply ranges between 0 and 3. And as the tribe hunts, the food supply will change depending on whether it hunts or not. So you can see that now the states are the amount of food. And then when you choose an action, hunt or not hunt, that amount of food will change. Okay. Okay, so I think someone asked whether I will record the tutorial. I'll probably will record the last tutorial on Tuesday. So if you need it, after next Tuesday, I will record it. And so you should see one by the end of Tuesday next week. So I still need to learn how to record it and upload it onto Waddle as well. But it will be recorded, don't worry. So let's go back to the question. So again, reading the first paragraph, now you should be able to derive the actions and the states. So there are three actions, there's two actions, hunting and not hunting, and there are four states which representing the food supply. Okay. So let me draw some stuff here. So remember, a state is represented by a circle. And in this question, there are four states that's representing the food supply. So let me draw four circles here. And maybe let me use different colors just to represent different things. So let me use blue to represent a state. So you have four states: state 0, state 1, state 2, and state 4. Okay. And again, and if you read the question, each state represents the level of the food supply. So here, this is no food supply, 1 unit of food, 2 units of food, and 3 units of food. Okay. And at every state, you can always take two actions. Yeah. Either hunt or not hunt. So let me, I think I might represent the action as a different color. Let me use black for the actions. And one thing that you will notice in this kind of diagrams is that the actions is duplicated. And then even though there's only two actions, but for every state, you have to duplicate the actions. So for this, if you're in state 3, you can take the action of hunting or not hunting. Okay, not hunting. Let me represent not hunting as red. So maybe I can write it up here somewhere. So red is actually not hunt, and black is hunting. And again, as I said before, you have to duplicate the actions because the transition probabilities are different, because the transition probability depends on the pair state action. Okay? So in state 1, you can also choose to hunt. If you're in state 0, you can choose to hunt. And then in each of these states, you can choose also to not hunt as well. Okay. Now, remember the arrow pointing, yeah, so someone asked, the tutorial is not recorded. I'm not going to record this tutorial, but I'm going to record the last tutorial, which is, so for each week, there are 3 tutorials. I will record the last one. Okay. And I mean, each tutorial is exactly the same anyway, so it should not matter which tutorial I'm recording. And the last one usually is the best one because I've already had 2 practices before that. Okay. And yeah, I guess if you want to record you can also record it yourself as well. Okay, so let's go back to the tutorial. Okay, so I was gonna say, so far we have 4 different states: 0, 1, 2, and 3. And then for each state, there are 2 possible actions: not hunt or hunt. Okay. Now, what's the next thing we have to do in this diagram? Well, the next thing is to find the reward. Yeah. Remember, for every so given a state and an action, you can get, you should be able to get a reward. So what's the reward here? What's the reward here, here, and here? So let's continue to read the questions. Let me skip the 3 bullet points. So these 3 bullet points in the question, they represent the transition probabilities. So we'll draw the transition probabilities later. Let's just go straight down to the last paragraph, which is the reward. So if the tribe does not hunt, the food supply will decrease by 1. And the reward function is the sum H plus L. So to get the reward, you have to sum up two values: the hunger reward and the load reward. Okay. Now, what is the hunger reward? The hunger reward is going to be 10 if before you choose the action, you have some food in your supply. Okay. So that means that if you look at this diagram here, if you have 3 unit food, then you definitely get a reward of 10 here. You definitely get a reward of 10 here. You definitely get a reward of 10 here. But if you have no food initially, then you don't get any reward at all. Okay? That's what this H variable means. Okay? And the same thing, it doesn't actually matter which action you choose. So notice how the H reward does not depend on the action. It actually depends on the previous state. Okay? So again, if you choose not to hunt, again, it doesn't actually matter whether you choose to hunt or not to hunt. The reward will always depend on the previous state. Okay? If there's there are 3 units of food before that, sorry, if there are 3 units of food before that, again, you get reward 10. If there are 2 units, you also get reward 10. If there's 1 unit of food, you also get reward 10. But then if there's no unit of food, you don't get anything. And that's H. So the next kind of reward is this L, this low reward. And the low reward will be 3 minus the full supply before you choose the action. And again, this low reward, actually, if you read this sentence, it also does not depend on the action. It also just depends on the previous state. And it's going to be 3 minus whatever the value of the previous state is. So if your previous state is 3, then your reward function, your low reward will be 2. Okay, 3 minus 1. If your previous state is 2, the reward will be 1. If your previous state is 1, reward will be 0. And this will also be 0. Okay, so I hope that makes sense so far. And then you do the same thing with the other action as well. Plus 0, plus 1. Again, you remember the reward does not even depend on the action. It depends on the state. Okay. So I think I've done I've labeled all the rewards. Okay, so there's only one more step to go, and that's the transition probabilities. Okay? So from a given an action, which states can I end up in, and with what probability? So let's now read the 3 bullet points in the middle. Okay? So it says that with probability 0.1, so Ethan asked, shouldn't I be 3 when supply is 0? Oh yes, sorry, my fault. You're right, actually. So it's gonna be the low reward will be the previous state minus, so it will be 3 minus the previous state. So 3 minus the previous state. I think I did it wrong. You're right. Okay, so let me erase this. I think I forgot to do the minus. So let me erase this guy, and start again. Okay. So 3 minus the previous state. So 3 minus 0 is 3. 3 minus 1 is 2. 3 minus 2 is 1. 3 minus 0 is 0. I think this should be correct. Sorry, not 0, and then that should be 1 actually. 1, and that should be 2. Okay, so it's 3 minus the previous state. Okay, so that was my bad. Okay, so let's continue. So now let's read the transition probabilities. So with probability 1, the food supply will decrease by 1 if possible. Okay? So that means that if you hunt, then there's a 10% chance the food supply will decrease by 1. Okay? So I think there's a 10% chance that I can go back to state 2. If I'm in state 2, there's a 10% chance I can go to state 1. And if I'm in state 1, there's a 10% chance I can go back to state 0. Okay. And then if I'm in state 0, then I can't get into negative state. So if not possible to decrease by 1, then I just remain where I am. Okay. So if I'm in this state here, I'm just kind of going back to my original state with probability 1. Okay, so this is just labeling the first bullet point. The second bullet point says, with probability 0.2, the food supply will remain the same. Okay, so there's a 20% chance that the food supply will remain the same here. There's a 20% chance that I will stay where I am here. There's a 20% chance I will stay where I am here. And now with state 0, there's a 20% chance I will stay where I am. But so that means that I'm actually adding this 20% probability to this arrow here. So now instead of 0.1, it's going to be 0.3. Okay. Yeah. So John asked in the chat box. So some of these arrows represent the rewards. Other arrows represent the transition probabilities. And the only way to distinguish between these two is you have to see whether the arrow goes from a state to an action or an action to a state. Okay. So if an arrow points from a state to an action, then the label of the edge represents the reward. If the arrow points from an action to a state, then that's its transition probability. Okay, so that's the only way you can tell apart. You need to look at the source and the target node. there are two arrows from state to state, then I think I did it wrong. Yeah, okay, so sorry, in that case, I should not point from state to state. So this diagram is slightly complicated, so we'll make mistake every now and then. So this arrow should really be point from, it always have to point from action to state. And yeah, so I think it should be like this. And I think that should be fine now. So that's another mistake that I'm making. Okay, so I think that looks slightly better. Yeah. And I think I accidentally delete the actions here. Okay. Okay, so I think that's looking better. Is there any more questions or any more mistakes I'm making? Shouldn't those arrows, someone asked, shouldn't those arrows go from hunt action above the state? You're right. So we haven't even actually talked about this guy yet. So this guy should really be like this. And this guy should really be like this. Okay. I think that should be correct now. Okay, so let's move on to the third bullet point. With probability 0.7, the supply will increase by 1 if possible, otherwise it will remain the same. So now, if we're in state 0, there is a 70% chance that we will go to state 1. Okay, so now I have to make sure that I'm pointing the arrow from action to a state like this. So the diagram is getting more and more confusing now. 0.7, and then if I'm in state 1, taking the hunt actions, there's a 70% chance I will go to state 2, and so on, and the same thing here. Okay. And finally, just be careful with state 3. There's a 70% chance I will stay where I am. I can't increase the state 3 anymore, so I have to stay where I am. So now, but remember that before, from the previous bullet point, there's already a 20% chance I will stay where I am. So I have to add this 70% to the 20%. Okay, so now this 20% will become 90%. Okay, so I think we're basically done with the probability, with the transition probabilities of the hunt actions. So this is the final step of these questions will be the transition probabilities of the not hunt options. So hopefully, I think this should be cleaner. So if I do not hunt, the full supply will decrease by 1 if possible, with certainty basically. So there's no probability, so that's nice. So if I don't hunt, I will definitely go down to the full supply will definitely decrease by 1 with certainty. So I think I don't even have to label here. You can actually add a 1 label here, but you don't have to. Okay? Because if there's only 1 arrow going out of an action, then that means that it will happen with certainty. Okay? There's an arrow going from here to here and an arrow going here to here. Okay? And then if I'm in state 0, I can't decrease the full supply any further. So I'm just going to stay where I am. Okay? Like here with certainty. I think we are done with these questions. So this diagram looks extremely confusing. I think I probably should draw some of the stuff below, not just everything above. But anyway, so that's this is question 3. Well, this is question 1. So sorry about some of the mistakes I'm making. I will probably continue to make mistakes throughout this tutorial. But any question about this? So I hope you guys. The whole point of this question is really to turn a set of descriptions into a transition into an MDP diagram. And really the key point here is that you have to be identify what the actions are and what the states are. Okay. Okay, so let's move on to the second questions. The second question is probably a bit more interesting because now it's not just mechanically turning a problem into an MDP diagram, but now it's about converting one kind of problem to a different kind of problem. So let me scroll down here. So if you remember in the lecture, I think this was probably in the first lecture, there are 2 kinds of problems that your lecturer mentions. The first is the MDP that we just talked about, MDP. And again, to remind you, we have set of state, a set of actions, a transition probability, and reward function. Now, there's a different kind of problem, which is called the stochastic shortest path problem, SSP. And it is almost the same as an MDP, except for two things. We still have a set of states. We still have a set of actions. We still have the transition probability. But instead of a reward, we now have a cost. Okay? And you can just think of the cost as just minus a reward. So it's nothing too fancy here. And then there's a new kind of object, which is the goal state, the set of goal state. Okay? And so one key difference between an SSP and an MDP is that in an SSP, the plan, or I guess the path you find is always finite because you have a goal. Okay, so you're always trying to find the shortest path from a state to some goal. Okay? And the question now is, I guess the problem now is to convert an MDP into SSP. And it turns out that the algorithms to do the conversion is fairly easy. So if you look at the slide, so this is in, so I can't show it on the screen, but if you go to the first lectures, I think it's on almost the last page, I think, of the first lecture. There is, so slide 28 of lecture 1, that will tell you the algorithms to convert, how to convert an MDP into an SSP. So there are 3 steps. You add a goal state, you add a transition probability from all the state to that goal state, and then you have to multiply the other transition probabilities just to make sure that everything sums to 1. Okay. So let me, I think, so to illustrate this algorithm, let me actually just go through an actual example, which is this question here. So in this question, you're asked to convert figure 2 into an SSP problem. So let me draw, let's start by drawing figure 2. So let me go down here. Figure 2 looks something like this. Okay, I think I can't actually scroll any down further, so I'm going to delete some of the stuff up here. Let me create a new page. Okay. So we have 3 states, S, T, and U. Okay, so we have S, we have T, and then we have U. And okay, so let me just draw this. So from state U, you have to take one action, and you will definitely get a reward of 10. And if you take that action, you will definitely go to state S, okay, with certainty. If you're in state S, you have 2 choices. You can either take this action up here with reward 1, or you take another action with no reward. And then if you take the first action, you will definitely go to state T. If you take the second action, then there's a 50% chance you will end up in state T, and then there's a 50% chance you will end up in state U. I think maybe let me use the notation, 0.5, it looks clear. 0.5 here, 0.5 here. And then I think there's one more thing I have to draw, which is from state T, you also can only take one action with reward 2. And then if you take that action, there's a 40% chance you will end up in state U. And there's a 60% chance you will kind of go to state S. Okay, so this is just a standard MDP, nothing too fancy. So now the problem, so now let's actually turn this into an SSP. So the first step when you do this conversion is to add a goal state. Okay? And let me use a different color here. Let me use blue. So let me just add this goal state all the way up here. Goal state. G. Okay. Now you can think of the goal state as just a way to tell your MDP to stop. Okay. So remember, the MDP can run forever. It doesn't have to terminate at any point. And the whole point of having this goal state is to say, well, at any time step, I can stop with some probability. Okay. So I'm going to add a transition probability from all action to this goal state. So in this diagram here, I have 4 different actions. So they're going to be 4 different transition probability. So from here to here, from this guy to this guy, from this action to the goal, and then that's one more action, which is this action here to the goal. I think I'm sort of missing stuff here. That's the edge of the page. Okay, and then we're gonna set the transition probability to the goal to be 1 minus gamma. Okay. Again, the intuition is really just about giving the system an ability to stop at any point. At any time step, you always have a 10% chance of stopping the game or the episode. Okay, that's the whole point of having this goal state. Okay. Now, what's the second step? The second step is to, or actually the final step, and the first step is to create a goal state. The second step is to set the transition probability of the goal state to be 1 minus gamma, which is, in this case, is 0.1. And the final state is really to make sure that the probabilities sum up to 1 again. Okay, so if you, let me actually just pick one particular action. Let me pick this this action, this guy here, okay? This top action. Now, if you look at this top action here, there are already two outgoing edges with probability 0.6 and 0.4. But now, since we're adding an extra edge here with probability 0.1, if you sum up all the probability, you get 1.1, which is not 1. So you really have to renormalize them so that they become 1 again. And the way to do that is to multiply the existing probabilities with gamma. So I'm going to add, and in our case, gamma is actually 0.9. So let me actually put it in the corner. Gamma here is actually 0.9. So I'm actually going to add gamma everywhere. Okay? And it turns out that if you do this, they will become they will become normalized again. They will sum up to 1 again. Okay? So for example, 0.6 times gamma is 0.56, 0.56. And then 0.4 times gamma is 0.45, 0.45, and so on and so forth. Okay. Okay, so someone asked in the chat box, the slide says that the transition probability from S to G from any state to a goal state is gamma, or is it 1 minus gamma? So I think it should be 1 minus gamma. Does the slide say gamma there? Yeah, so the slide actually has it the other way around. I don't know why. It should be, maybe there's a mistake for the slide. So it should be 1 minus gamma. So it's kind of like you want a small probability to, the intuition really, at every time step, you just want a small probability of finishing the episode. That's kind of the intuitions. And gamma is usually very close to 1. So you want the probability to be small, so you want to take 1 minus gamma. And then the final step is to add, to basically multiply all the existing probability with gamma. And I think I just want to quickly show you that it actually works. So if you are not convinced that what we're doing here results in a normalized set of probabilities, then just suppose that initially you have these two probability A and B, and initially they sum up to 1. And then suppose you add, and what we're essentially doing is that we're adding everything we multiply all the existing probabilities with gamma, and then there's an extra 1 minus gamma probability of ending up in a goal. And I claim that this new sum will be 1. Okay? And I think you hopefully you're convinced that this is 1. Because this is, I think A plus B is 1, therefore we have gamma plus 1 minus gamma, which is 1. And so someone asked, so should the probability be swapped? The answer is yes, it should be swapped. So I will double check with Obong. It has to, the transition probability to the goal has to be 1 minus gamma. It has to be a small probability. Okay, so any other questions? So I hope that, I think you don't have to know the proof of this. So you can probably prove that, any solution or any optimal policy that's found in this stochastic shortest path is also an optimal solution in the original MDP. So it's probably, you should be able to show that with some math, but let's not worry about that. Yeah, but let's just as long as you get the intuition behind this, that is that at any step, there's a small probability of ending, of going to the goal. That means that's the same as just ending the episode. And then we have to just renormalize all the probabilities again. Okay. So John asked, why is there an arrow without a number leaving S? Leaving S, there's an arrow. So yeah, so if there is nothing labeled in the edge, that means that there's no reward. So that's the same as having a 0 here. And I think it's the same thing in this guy from the first action of S to state T. Okay? So if there's no label from an action to a state, that means that the transition probability will be 1. And then if there's no label from a state to an action, it means that the reward is 0. Okay, that's just a convention. And I think the here as well. Oh, actually, I think I have all the labels now. So I think that's basically question 2. Okay, so someone asked why the probability to the goal is 0.1. Where does 0.1 come from? So 0.1 is 1 minus gamma. So in the question, gamma is given to you as 0.9, and therefore 1 minus gamma will be 0.1. And the algorithms tells you that it basically just tells you that set the transition probability from any action to the goal to be 1 minus gamma. Okay. Which is again, the intuition is just think of that as a small probability of ending the game. Okay, so someone asked, do we need to change anything about the rewards cost, given that we're minimizing cost instead of maximizing rewards? Yes, and there's actually also one more step, which is the 4th step, where you set the cost of your SSP to be 1 minus the reward. Okay, this is the final step. In fact, there's one more thing I have to do here that I forgot to do, which is to add a minus sign everywhere. So minus, everywhere there's a reward, I have to add a minus sign. So minus sign here, minus sign here, minus signs here. And I think that should be it. So I did forget the last step of adding a minus sign. Okay? Because now we have minimized the cost instead of maximizing the reward. So I hope that's clear. Okay, so if there's no question, we can move on to next part. Okay, so question three. It's very, very short. So question 3, you just have to come up with an optimum policy that is non-Markov. So there's an infinite number of ways to do these questions. So the way to make something non-Markov is just to make sure that your policy depends on the previous 2 steps instead of just the previous step. And you just make it. It's as simple as that. It's a bit more tricky to making sure that it is optimal. So let me just scroll down here. So I think the way to do this, if you think about it, is you want to start out with, again, so let me just state the problem. Maybe let me create a new page here and state the problem. Okay. So I want to design a non-Markov optimal policy. And so the way to do that, if you think about this, is that suppose you start with some state V here. Let me start something, and I'm going to create 2 branches. Okay? And the idea is that it should not matter whether I take the upper branch or the lower branch, the upper action, let's call that D, or the lower action, let's call this E, and the reward should be the same. Yeah? That means the value, the Q value for VD should be the same as the Q value from VE. Okay. And so if I do this, then I now can create a policy where whether I take state D or state E will depend on the previous two steps. Okay? But it doesn't matter which one I choose because they will lead to the same actions. Okay? So let me now add some state before this. Okay, so let me, suppose I'm going to start with state S here. From state S, I have to take an action A. And then from action A, there's now two possibilities. Go to state T or state U. Okay. And with equal probability as well. And now from each of these states here, again, I have to take one action that will end up in V. Now, so one kind of policy, non-Markov policy, so let me just write down a non-Markov policy is that at state V, so at V, I'm going to take action D if I come from state T. Okay. Else, I will take action E. Okay. That's kind of the high level thing. So if you just look at this policy here, this is actually a policy. Okay? It's a policy written in English. But if you look at this policy, this is definitely non-Markov because whether I take action D or V, it's not enough just to know that I was in state V in the previous step. I have to know where I was in the previous two steps. Okay, so that this is definitely non-Markov. Non-Markov. Now, the more tricky part is to make sure that it is optimal. Okay, so to make sure that this policy is optimal, the easiest way is to ensure that it doesn't matter whether I take action D or take action V, the value will always be the same. Okay, so suppose that I think the easiest way here is actually just to make sure that this is, you get the same reward here. That's one way. There are more fancy ways, so let me actually try a more fancy way to show you guys some nice, basically just to show you guys the geometric sum. I think the geometric, you actually see the geometric sum every now and then in reinforcement learning. So I'm going to add some new state, W. And then if I take action D, I will definitely go to state W, but then I will get stuck in this state forever. Okay. If I take any action, I will just go back to what I am. Okay. And same thing with state E. So same thing with action E. If I take action E, I will end up in a different state where I will get stuck in forever. So it's like an absorbing state if you think about it. Now, if I set this, suppose that if I end up in state W, I don't get any reward. And if I end up in state X, I get a reward of 1 here. Then would you be convinced if I tell you that the value of V will be the same? Doesn't matter which path I take. So if you think about this, suppose that I take, I'm in state V and I take action D. So let me scroll down here. If I'm in state, yeah, okay, maybe here. So if I'm in state, not enough room. Okay, let me write it up here. So if I'm in state V and I take action D, then what's the reward? The reward is definitely 1, okay? Because I get a reward 1, and then after that, I don't get any more rewards afterwards. Now, what if I'm in state V and I take action E? Well, initially, I don't get any reward, but after that, I will get a reward of 1 and 1 forever. Yeah, will keep getting a reward of 1. But don't forget, there's also a discount factor as well. So 1 gamma here, and then I get another reward of 1. And because I keep looping between this X and G. Yeah, I get another reward of 1, but now I have discounted twice, and so on and so forth. So this is like an infinite sum. Yeah. And as a fun result, you might know that if you sum up all these gammas, so gamma to the power of k, where k starts from 1 to infinity, that will give you back. Well, actually, it will give you 1 over, I think I had to start with 0 here. It will give you 1 over 1 minus gamma. Yeah, this is the geometric sum. For those who are interested in this is called the geometric sum. And now in the special case, if I let gamma to be 0.5, then this summation here, if I start from 1, because here I'm actually starting from 1, I don't have the 1. The first item is actually 0 to infinity, 0.5 times power of k, that's going to be 1 minus 1 minus 0.5 minus 1, which is going to be 1. Okay. I think that's 1. So that's just a fun result that you might want to know. Well, the thing that you probably want to know, and especially if you want to prove certain things in MDPs and reinforcement learning, is actually this geometric formula that we'll use every now and then. Okay. But anyway, I think now I have a non-Markov optimal policy. Why is it non-Markov? Because of this condition here that an action depends on the previous 2 states. It's optimal. Well, I just show you guys that it doesn't matter which path I take. I always get the same reward. Okay. So I hope that kind of makes sense. Any questions? Can I just scroll down again? Okay, so let me scroll down like this. Okay, so I think that's the first part of this question. So the question is very short, but it takes a while to go through. There's another part of this question as well. So we've done the first sentence. There's the second sentence says, how do we transform, or actually maybe someone asked, why do we have a -1 in the second value? We have a -1 in the second value because we're starting counting from 1 instead from 0. So this formula is given to you. So I guess you can prove it. There's proof online if you search on Google. So if I kind of, maybe if I start k from 0, then there would not be a -1. It'll be like this. But because k starts from 1 here. Okay. And the reason why k starts from 1 is because in here, and we don't get any reward initially. So if in this part here, if I change this to a 1, then I would start counting from 1. What's that? Because remember, 0.5 to the power of 0 is 1. Okay, so actually the series should start from 1. The series, the formula for the geometric sum, the way that it's usually presented. Sorry. Siri thought I'm saying something. Okay, sorry. So if you kind of look at the textbook and on the Wikipedia, for example, and we look at the geometric sum, the way that they present it usually has k starting from 0. Okay. Okay, so so the next part of this question asks you, how do you transform that non-Markov optimal policy into a Markov optimal policy? Okay. So remember, we have this policy here. How can I make it Markov? Okay. Well, an easy way to do this is actually just to pick a particular path. So and in fact, it doesn't really matter which path you pick. So I'm actually gonna let me circle the top path. Let me just pick the first path. So that what it means is that now my new policy would just be always taking the action D. Okay? And I claim that this is optimal. Okay? So, and I think intuitively you can sort of see why it is, because if this action was not optimal, suppose that there's another, I guess, another optimal policy where I'm not sure if the proof would be obvious. So and I think the way you prove this is just a proof by contradiction. So if you can show that if this policy is not optimal, then you can kind of replace the previous policy here with a new policy that's even better, which contradicts your initial assumption that your initial non-Markov policy is optimal. Okay. But in general, the general principle to turn something non-Markov into a Markov is just to pick one, just pick a particular path. Yeah? It should not matter which path you pick, you just pick one path. And that will be an optimal policy. Okay, I think that's all you have to know. You don't have to worry too much about the proof. So this course is, you can think of this course as more of an overview. It actually just gives you a quick overview of a lot of different topics in reinforcement learning, but it doesn't go deep, go into depth in a lot of these concepts. Any questions? I think we're done with question 3. And actually, there's another a similar theorem for this question. So this is one way to turn a non-Markov optimal policy to a Markov optimal policy. You can also use a similar principle to turn a non-deterministic optimal policy into a deterministic optimal policy by just picking an action. You can pick any action with a non-zero probability, and that will also give you an optimal deterministic policy. So that's just a similar principle you might want to apply. Okay, so maybe one more question. I think I probably definitely will not be able to do question 5 this week. So the last question, the dead end question, will be left until next tutorial. Question 4 on value iteration. This question, the goal, the punchline of this question is that it doesn't really matter what the initialization of your values is. You will, as you go through this value iteration algorithm, you will always end up with the same value at the end. That means that you always converge to the same value. Okay. Now, someone asked a question about the previous, about question 3. So for Markov, we can have a policy state action instead of policy history actions. Yes, that's right. So that's that's what a Markov policy means. It means that it only depends on the current state, not on the entire history. That is the definition. That's right. And the way to do this in this question is basically just to pick any history path. Okay, so let's go back to question 4. In this question here, and as I said before, the punchline is really to say that it doesn't really matter what the initial values is. You will always converge if you go through the value iterations. I think, do I have enough time? So this question, I think I might. It's 152 now. So I think this question, maybe I might leave it for you guys to do this week. So this question would be quite fun to do using Python. So you can just write some short code and just to convince yourself, implement value iteration and convince yourself that you actually end up with the same value at the end of the day for all different states. It doesn't matter whether you start with 0 or start with 100 or start with 1,000. You will always converge. It might take a while to converge, but you will definitely converge. Okay, so that's one thing to do. And maybe I think next week I will probably show you the Python code to for the value iteration. We'll just implement this using Python dictionaries and loops and for loops. Nothing too fancy actually. So you don't need any special libraries to show the convergence. Okay. So we'll leave that for next week. And then for the dead end questions, again, it's an interesting problem, and it's also for next week as well. So I think I only have a few minutes left, so I think I might just stop here. And I will see you guys next Thursday. Okay, so if you don't catch this, I will repeat the same tutorial at 3 o'clock and the same tutorial on Tuesday next week as well. And I will record the Tuesday tutorial. Okay. So anyway, I'll see you guys next week. I will stop.